Hi. In the previous video, I have discussed different kind of forces. And so depends on the situation, there are different kind of forces exerted. And it is not always that you only have one force exerted. There are many cases that there is an object, either it's at rest or even if it's moving, there are multiple forces exerted. And when we see, so then what we see is the resultant after having that many forces acting on it. What we see is the resultant. And the resultant force is called the net force. So when you hear net force, that means it's a resultant force from multiple, more than one forces exerted on an object. Let me go into the screen. Here. So often you see an object and you have multiple forces exerted on the object. There are cases that multiple forces are exerted on the object. And we say the net force, which is the resultant force. So we write the net force like this. This is how we write the net force. This is the net force. This thing, this yellow highlighted thing, this is a Greek letter sigma. This is a Greek letter. Uppercase sigma, which represents the sum. It's the sum of all the forces. So let's see. Let's look at it. For example, let's see. There is a book that's at rest on the table or desk. Let's say here is the book. So here is a book on the table, the surface of the table, right? And you see that this book is on the table and the book is at rest. So here is a notebook that's on the table and then it's at rest. So what we see that this book is at rest. Okay. So when the book is at rest, it looks like it's not moving. It's stationary. So therefore, it doesn't look like there's any force that's applied. Force means either push or pull, but it's the resultant force is zero. It doesn't mean there is no force applied. So it's the resultant of multiple forces that's exerted on the book. When you add up all the forces, it's zero. That's why the book is at rest. So we write, in this case, we say the net force Okay, this pen is going. The net force is 0 because the book is at rest, right? And what really is that the net force resultant force is 0. So what are the forces exerted on the book? Is there no forces exerted on the book? No. There's always gravitational force exerted on a book, right? Any matter on the surface of the earth, we have a gravitational force. And do you remember from the last video, what is the direction of a gravitational force? The direction of gravitational force is vertically downward. So let's draw that arrow, okay? Also, force, is that a force a vector quantity or scalar quantity? Force is a vector quantity. So therefore, we can represent those vector force vectors as with arrow. So in the middle of the book here, I'm gonna draw gravitational force vector, which is vertically downward. So vertically downward, and make sure I label this is the gravitational force, which is vertically downward. What else is the force exerted on the book? This book is in contact with the surface of the table. And whenever you're in contact with the surface, you're always gonna have what kind of a force? Normal force, right? And normal force, do you remember the direction of normal force? The direction of normal force is always perpendicular to the surface. So let's draw the normal force, or you can also say a support force. I'm going to just use the same color. Normal force is always perpendicular to the surface. So in this case, the table is horizontal. So it's going to be perpendicular to the surface. If the table is slanted, the normal force is going to be pointed in this direction. But in this case, it's like this. What do you think is that? So that's the direction of a normal force. But how about the magnitude of the normal force? What would you guess? Do you think that normal force arrow should be longer than a gravitational force arrow that you draw? Or it should be shorter? Or the length of the arrow doesn't matter? That's right. The normal force, the length of the arrow of the normal force should be the same length as the gravitational force. So when we draw the normal force here, we're going to draw upward. And then again, I make sure I label it. And the length of the normal force should be about the same as the gravitational force. Because, are there any other forces exerted on this book now? This book is at rest on the table. No, there's no other force. There's no other forces. So these are the two forces that exerted on the book. And you see that forces are vectors, right? Force is a vector. So therefore, you have two forces, but you don't just add the magnitude of the forces, gravitational force and then normal force. You got to take into account of a direction, and that these two forces are pointed in a completely opposite direction with the same magnitude. Therefore, the resultant force, which is the net force, is equals to 0. So I can write this like this using the symbol that we just used here. This means the net force, which is also the same thing as the sum of all the forces exerted on the book, right? Is equals to, we have gravitational force plus the normal force. Okay, and when I draw the arrow on top of the symbol of a gravitation Fg and N, that means it's a representation of a vector. So I could write 5 Newton. No. So that means it's a representation vector. So it's including the information about the direction. So I could just write Fg plus N. That's taking into account of N and Fg can be in an opposite direction. And I can just simply say this is equals to, what is the value? Gravitational force plus the normal force is equals to 0. All right. So the net force, again, the idea of a net force means you just add up all the forces. That's what it means by net force. You could be having a case that a vector that's a force that's pointing in one direction, and then a force that's pointing in another direction. Another example. Can you find the net force? For example. But anyway, in this case, the first example that we just did about the book that's on the table, is at rest on the table, we have a net force to be 0, right? So although it looks like the book doesn't have any forces applied, it's just stationary, it's because the resultant force, the net force is 0. It doesn't mean that there are no forces exerted. And so that's the idea. We call this, when the net force is equals to 0, we call this equilibrium. So here is another terminology, equilibrium, right? What I mean actually is the mechanical. It's in mechanical equilibrium, because equilibrium can be thermally, in a thermal equilibrium and other kind of equilibrium. So in this case, what we mean is the equilibrium. What equilibrium is when the net force is equals to 0. So when you have an object that's its net force is equals to 0, we say that object is in equilibrium. Okay. So I'm going to highlight it. It's very important. This is also important too, but the net force is also important. And mechanical equilibrium means that when the net force is equals to 0. So go to the next page. Let's see. I have it in black. Okay. So I writing again, mechanical equilibrium. That means that net force equals 0. Or if you add up all the forces exerted on the object, it turns out that total force is 0. And there are two kinds of equilibrium. One is called static equilibrium. The other is called dynamic. Either way, the net force is 0. Dynamic equilibrium or static equilibrium, net force is 0. Equilibrium means just net force is equal 0. So I can again write it here. Okay. Just say net force equals 0. Net force equals 0. Static equilibrium is net force is equal 0 and the object is at rest. Oops. What's going on? No. Static equilibrium, here, sorry, is object is at rest. So it's like the case that a book is on top of the table. That's when the we can say the book is on static equilibrium. I can also say here, there's a pen that's at rest on my hand. Does that mean that there is no forces exerted on the pen? No. There are forces exerted on the pen right now, even though it's at rest. There is a gravitational force that's pushing the pen down, vertically downward, and my hand, the palm of my hand is pushing this pen up, perpendicular to the direction of my, on the surface of my hand. And they're equals to each other and in the opposite direction. Therefore, the sum, the total force is 0. And we call that this pen is in static equilibrium. So when the object is at rest, when it's not moving, that object is at static equilibrium. There are cases that an object is moving and still in equilibrium. Even though the object is moving, when you add up all the forces that's exerted on the object that's moving, it can be the total force is 0. Such a motion, when the object is in dynamic equilibrium, when the net force is 0 and the object is in motion, that motion should be in a constant motion. Constant motion means that it's moving in a steady speed in a straight line without any change, just moving smoothly. When the object is moving smoothly, when the object is moving steady in constant motion, that means that same speed, constant speed, no change in speed. It doesn't go faster or slower, just moving, continuously moving, and in a straight line. No change in direction. So when the object is moving, but if it doesn't change the direction and then no change in speed, we can say that, okay, the total force, there could be a forces exerted on the object or maybe not, but the total force is 0. That object is in dynamic equilibrium. Sometimes you can see, or even the ice, you can have an ice and then it melts a little bit. So it becomes really slippery on the surface. So you have almost 0 friction. And then you just push the ice on the surface, on the smooth surface. Ice is going to just slide without changing the motion, slides. That ice is in, the cube of ice is in dynamic equilibrium. It's moving constant speed in a straight line. Or case is you push it, you push the, let's say you push. Oh, he's got so many legs. You push the object and then it's hard to move, it's hard to move, it's hard to move. So it doesn't move, but then it may start move. It's if you push it harder and harder and harder, it starts moving. It starts moving and moving and moving. But you don't have to push. You could move it with the constant motion in a straight line. That means that push force, the normal force from your hand, the push force, which is the normal force from your hand, right? F push is this way. And what else is the force exerted on this box in a horizontal direction of motion? It could be moving, so it's in motion, moving steadily. It's a steady motion, this box. So you have a push force, and there is another force, which is friction force. They happen to be equal in magnitude in the opposite direction. And then you have a gravitational force, which doesn't do anything to the motion, but Fg, and then the N. Also, so in this case, when you have a push force, the normal force from your hand, and also the friction force on the box, when they're equal and opposite each other, this box is going to be moving in a steady motion, steady speed, and in a straight line. And let me see. Moving, steady motion. And that case, we say that this box is in F push. So if we say F push plus the friction is equals to 0, that means that in this case, the net force in the horizontal direction is equals to 0, right? So it's in dynamic equilibrium. The box is in dynamic The box is in dynamic equilibrium. You can apply a motion, but then if there's a friction force that's in the opposite direction that's equal, then in magnitude, then the box is in a steady motion, then it's moving, but it's in dynamic equilibrium. So either way, when you add up all the forces and the net force is equal 0, we say the object is in equilibrium. So I guess this would be the end of the video. I could discuss a little bit more about static equilibrium in a separately, and also the dynamic equilibrium separately. So I'll see you in the other videos and in a discussion.